We will now discuss a very important topic in functional analysis, namely spectrum of an operator. You would have already heard of this word from linear algebra, where they given a matrix. Its spectrum is a set of all eigenvalues. So we generalize this notion. So we will briefly go back to Banach spaces, and now we will work with a complex field as the basis. So V Banach over C. Okay, and T belongs to LV. So it's a continuous linear operator on V. So we have a definition. The spectrum of T sigma T is defined as sigma T equals set of all lambda in C such that T minus lambda I is not invertible. The resolvent, so the spectrum of T, the resolvent of T is so denoted rho of T is defined as the complement. So rho of T equals set of all lambda in C such that T minus lambda I is invertible. Okay. So we want to study the properties of the spectrum of a given operator. Okay, so suppose T belongs to LV and norm T is less than 1, then we know that we have shown this in an exercise that I minus T inverse exists. So, and in fact we have shown that I minus T inverse is nothing but I plus T square plus etc plus T power n and so on. That's the infinite series. Okay, so if you now take the norm of this, so you get norm I is 1 plus norm T square plus norm T power n and so on. That's the geometric series with norm T which is less than 1, which is convergent, and so that immediately tells you that norm of I minus T inverse is less than or equal to 1 by 1 minus norm T. Okay. So also recall something else which we have done. So let us take T invertible, okay, and S in LV such that norm S is less than 1 over norm T inverse. Then look at T minus S. This can be written as T into I minus T inverse of S, and norm of T inverse of S is less than or equal to norm T inverse norm S. Norm S is less than 1 by T inverse, so this is strictly less than 1. So this is invertible and this is also invertible, implies T minus S is invertible. So from this we saw that so invertible operators in LV form an open set. So if rho belongs to, so if lambda belongs to rho of T, that means T minus lambda I is invertible, then this implies that lambda of plus delta is also in rho of t for delta sufficiently small, because invertible operators form an open set. So this implies that rho t contained in C is open, implies sigma t contained in C is closed. So the spectrum is a closed set. Okay. So now assume that mod lambda is strictly greater than norm t. Then what is t minus lambda I? This can be written as minus lambda times I minus lambda inverse of t. Okay, and norm of lambda inverse of t is mod lambda inverse times norm t, and mod lambda, and this is again strictly less than 1. Okay, because mod norm t is strictly less than mod lambda, and therefore this is strictly less than 1. So this again, this becomes invertible. Therefore mod lambda greater than norm t implies that lambda belongs to rho of t. So lambda belongs to sigma t implies mod lambda should be less than or equal to norm t, and therefore sigma t is contained in the set of all lambda in C such that mod lambda is less than or equal to norm t. So it's a bounded set, it's a closed set, so sigma t is closed and bounded, that is sigma t is compact. So the spectrum is a compact subset of the complex plane. Okay, so now definition again. Okay, so let B bar 0R equals closed ball, center 0, radius R in C, and then you have that consider R of t equals inf of set of all R greater than 0 such that sigma t is contained in B0, B bar 0R. Then RT is called the spectral radius of t. Okay, and then of course you know that RT is less than or equal to norm t. Okay. So now we want to show that the spectrum is in fact a compact set, but it's a non-empty compact set. So the elements always exist in the spectrum. Okay, so let us try to show that. So let lambda belong to rho of t, and then you define therefore t lambda equals t minus lambda I inverse. Now you can write t lambda also in this fashion, that is lambda, I am going to pull out the lambda, so since there is an inverse outside, it will become lambda inverse into 1 by lambda times t minus I inverse. So if mod lambda is greater or equal to norm t, you have norm t lambda is less than or equal to 1 by mod lambda, and then this mod lambda is less than norm t, so this norm of t by lambda is less than 1, and you know you can estimate the inverse, we have already done that, that's 1 by 1 minus norm t by lambda. Okay, so this means that norm T lambda is bounded and tends to 0 as lambda tends to infinity. Okay, so this is as mod lambda tends to infinity. Okay, so this is an observation which we will make. Okay, now let lambda and mu belong to rho of t. So T lambda I am going to write as T lambda times T minus mu I times T mu. So T minus mu I, T mu is nothing but the inverse of T minus mu I, and so that's identity. So T lambda is this. So this we will write as T lambda into T minus lambda I plus lambda minus mu times I into T mu. I have just added and subtracted a lambda I in this equation. So if I now multiply it, T lambda is the inverse of T minus lambda I, and therefore this will be I plus lambda minus mu times T lambda T mu. Therefore we get T lambda minus T mu equals lambda minus mu times T lambda T mu. So this is called the resolvent equation. So now let f be a continuous linear functional on LV. So LV stars, f belongs to LV star. Define phi of lambda equals f of T lambda for lambda belonging to rho t. So it's defined on an open subset of the complex plane, and you get this. Then mod phi lambda is less or equal to norm of T lambda, and we saw that norm of T lambda already is a bounded thing, and in fact it goes to 0 as lambda tends to infinity because of this particular relationship here. So therefore you have that this is bounded and it goes to 0 as lambda tends to mod lambda tends to infinity. Further, if you take phi lambda minus phi mu by lambda minus mu and let limit as lambda tends to mu, what do you get? So from the resolvent equation, this is nothing but phi of f of T mu square. This is just, sorry, T mu square is an operator, f acts on it. So it goes as lambda goes to mu, so T lambda, phi of this is phi of T lambda minus phi of T mu by lambda minus mu is phi of T lambda T mu as lambda tends to mu, and therefore that goes to phi of T mu, f of T mu square. Therefore we have, that means phi defined on rho t is differentiable at each point of rho t. It is bounded and tends to 0 as mod lambda tends to infinity. So now we get a nice contradiction. So if sigma t is empty, this will imply that rho t equals whole of the complex plane, and this will imply that phi is an entire function which is bounded, and by Liouville's theorem this means that phi is a constant, but phi lambda goes to 0 as lambda tends to infinity, and therefore this implies that phi is identically 0, but that is absurd because phi is identically 0, and this is true, that is f of T lambda equal to 0. This is true for any f in LV star, but the dual separates points, so this implies that T lambda equal to 0, and that is a contradiction. T lambda is the inverse of an operator, it cannot be the 0 operator. Okay, so this proves, so this implies that sigma T is a non-empty compact subset of C. So remark, so C is important. For instance, if you took only R, then look at the matrix 0, 1, minus 1, 0, then what are its eigenvalues? So the characteristic polynomial is lambda square plus 1 equal to 0, so lambda equals plus or minus I. These are the only eigenvalues and they are not real, and therefore sigma T in R as a subset of R, then you have sigma T is empty. So the spectrum could be empty if you are stuck to the real field, and that is why if the spectrum to be non-empty, you need that you have to work with the complex numbers. So that is the important thing. Okay, so now we want to see how the spectrum looks like. Okay, so definition. So lambda, so we have V Banach and T belongs to L of V and lambda belongs to sigma T. So lambda is called an eigenvalue if the null space of T minus lambda I is not equal to singleton 0. Okay, so that means, and if u not equal to 0, u is in the null space of T minus lambda I, we say u is an eigenvector of T corresponding to the eigenvalue lambda, exactly as we did in the finite way. Okay. And the dimension of the null space of T minus lambda I, this is called the geometric multiplicity of the eigenvalue lambda. Okay, so this is called geometric multiplicity. There is something else called algebraic multiplicity, which we can discuss. Okay. So now let me briefly recall a theorem which we have done before. Okay, so if V and W Banach, so recall. And A belongs to LV. Okay, then we showed that NA is range of A star perp. N of A star is range of A perp. Then we also showed that the following are equivalent. Range of A closed, range of A star closed, range of A equals null space of A star perp, and range of A star is null space of A perp. We also proved the following theorem, namely A on 2, that means range of A equals W, then there exists a C positive such that norm A star phi is greater to C times norm phi for all phi in W star, and 3, A star is 1 1 and range of A star is closed. Okay, these three, that means we have shown the equivalent. So similar theorem for A star on, with A star replacing A replacing A star, you have an identical theorem that I left as an exercise. So we have proved all these things. So now let us say A is 1 1 on 2, and of course it's continuous, and therefore A is an isomorphism. Okay, so then what do you say? So A is 1 1 and range A closed. This implies that range of A star is closed. Okay, and range of A star is nothing but null space of A perp. Okay, and null space of A is 0, that is 0 perp equals W star. Okay, so A star is on 2. Okay, let me repeat this. So A is on 2, therefore you have that. So this implies that A star is 1 to 1 and range of A star is closed. Okay, so range of A star is closed, and therefore you have that range of A star is equal to null space of A perp, but A is given to be 1 to 1, this is 0 perp, which is equal to W star. So this implies that A star is also 1 to 1 and on 2 and continuous, of course, and therefore it's also an isomorphism. Conversely, A star 1 1 on 2, so this will imply that A star is on 2, therefore A is 1 to 1 and range of A is closed, and you have range of A is null space of A star perp, and that's given to be 0, so 0 perp, and therefore that's equal to W. So this implies A is 1 1 on 2. So A 1 1 on 2 if and only if A star is 1 1 on 2. Okay, so this is a thing which we want to remember. Okay, so proposition H Hilbert space. So we are now in a Hilbert space. T is in L of H. Then lambda belongs to sigma T if and only if lambda bar belongs to sigma of T star. Okay. So what T minus lambda I adjoint is nothing but T star minus lambda bar I. That's it. So lambda will belong to the result. So this will be invertible. So T star minus lambda bar I invertible if and only if T minus lambda I invertible, and therefore lambda belongs to sigma T if and only if rho T and sigma T, they are the complements of each other. So this lambda bar belongs to sigma T star. Okay, so that is the thing. Okay, so let us take an example. Let V equal to little l2. So you consider the map X going to S of X. This is the shift operator. We have already seen this. This is X2, X3 and so on. So where X is X1, X2 So norm of Sx in 2 is less than or equal to norm x in 2, and therefore implies norm s is less than or equal to 1. But in fact, if you take E2 or E3 for instance, and then the shift will be E1, if it's E2 then the shift will be E1, and therefore norm of Sx will be equal to norm of x, therefore in fact norm s equal to 1. Okay, so this means sigma of s is contained in the set of all lambda such that mod lambda is less than or equal to 1. Now you take lambda equal to 0, then S of E1 is 0 because you start with E1 then you get 0. So E1 is an eigenvector and lambda equal to 0 is an eigenvalue. Now let lambda not be equal to 0 and then you consider Sx, if possible. Let's see if we can find Sx equal to lambda x. Now then this implies for all I greater than or equal to 1, xi plus 1 will be lambda times xi, and so inductively this will give you lambda to the I minus 1 x1. Okay, so but x belongs to L2, that means xi tends to 0, and therefore this implies that mod lambda has to be strictly less than 1. Okay, in fact let mod lambda be less than 1 and consider x equals the sequence 1 lambda, lambda square, etc. Now then x belongs to L2 because mod lambda is less than 1, you have a geometric series for the norm, so that is fine. So x belongs to L2, and if you take Sx is in fact equal to lambda x. Okay, so every lambda such that mod lambda is less than 1, whether it's 0 or non-zero, is an eigenvector. Therefore sigma t contains lambda such that mod lambda is less than 1, and sigma t is contained in mod lambda less than or equal to 1 and sigma s, and therefore so this implies that sigma s is in fact equal to set of all lambda such that mod lambda is less than or equal to 1, and so mod lambda equal to 1 implies lambda belongs to sigma of s, but it is not an eigenvalue. Okay, so the spectrum contains a whole continuum of points, unlike the finite dimensional case where the spectrum consisted only of eigenvalues and they were discrete, n discrete depending on the dimension, whereas here you have a spectrum of this operator which is a whole continuum of points in the complex plane, the entire disk, closed disk, and in that you have uncountably many eigenvalues and uncountably many members of the spectrum which are not eigenvalues. So every member in the interior of the disk is an eigenvalue, every member in the boundary is not an eigenvalue. Okay, now you define T of x equals 0, x1, x2 and so on. Then we have already seen this before, so check again. T star equals S and S star equal to T. Okay, you can check this. Okay, so then this is, so that is called, S is called the left shift and T is called the right shift. Okay, so now by the previous proposition, if lambda is in the spectrum of one of them, lambda bar should be in spectrum of the other. Now this unit ball, closed unit ball in the complex plane is symmetric with respect to conjugation. Therefore, sigma of t also has to be set of all lambda such that mod lambda is less than or equal to 1. So we just deduce it directly from the previous. We don't have to do anything. Now if you take tx equal to lambda x, so then what happens? So 0 equals lambda x1, then x2 x1 equals lambda x2 and so on. Okay. So if lambda is not 0, this implies xi equal to 0 for all I. Therefore, lambda not equal to 0, not an eigenvalue. Again, lambda equal to 0 is also not an eigenvalue because t is 1 1. It's an injective map, therefore it cannot have any non-zero vector going to 0, and therefore t is 1 1. Therefore, no eigenvalues. So you have a spectrum which is fully closed unit ball, but there's not a single eigenvalue for this one. So we have that the spectrum can behave really strangely, this thing, because in the finite dimensions 1 1 if and only if on 2, and that is equivalent to invertibility. In infinite dimensions, invertible may fail in many ways. Okay, it may be 1 1, it may not, it may be on not 1 1, it may not be on 2, etc. So that is why you have that the spectrum is 6. So we will continue with this.